Okay, so this is lecture 12. This will be another fairly short unit where I'm just going to focus on the question of how do derived rules work. So these rules that go beyond our basic rules. So our basic rules are, remember, in short, we have, roughly speaking, two rules for each connective. So we have, conditional proof and we have modus ponens. Those are the two rules for the if-then connective. We have and introduction and elimination. We have or introduction and elimination. Okay, it's a very Spartan set of rules. What that means is, as proofs get more complex, you have to do lots of repetition of application of those basic rules. But what you'll find is you'll find that often you're doing the same patterns again and again. So it would be really nice if you could name those patterns and then just, instead of repeating the whole thing, know that it could be repeated and then just say the name. So in real life, of course, even among professional researchers, it's very rare that one would actually go all the way back down to basic rules. So the key to effective communication and clarity is communicating to your audience, I know that I could fill in the steps here, and they can be convinced that you could, in fact, do that. So that's derived rules. The technical name for how these derived rules work in our system is cut. And cut basically is a pattern that says, if you have a bunch of proven sequence, those can be put together and give you something new. So again, rather than describing it abstractly, let me describe it concretely. Okay, so the following can be proven fairly easily just with basic rules. Okay, and in fact, again, it might not be a bad idea to pause the video to write the steps in between step 2 and line N that I have here, writing it in. Okay, the best strategy for this proof is it's a straightforward conditional proof. You assume P, then you derive Q, and from Q you derive R, and so then you do conditional proof, if P, then R. It will then depend just on lines 1 and 2. If you follow that recipe, the final step would be conditional proof, but that's not terribly relevant here, so I'll just leave a question mark about what the final step was. What's relevant is the fact that what you have is this thing on the right, if P then R, follows from the two sentences on the left. And what that means, of course, is you've established the following sequent, if P then Q, and if Q then R. From that, if P then R. Okay, so that's what you've established here. Okay, now what that means is we have effectively a derived rule. Here's how the derived rule looks. The derived rule says now, okay, so the one thing to notice is this, our ability to prove this sequent here doesn't, again, depend on the identity of P, Q, and R. You could replace P throughout with the same sentence. You could replace Q throughout with the same sentence and replace R, and the proof would still go through. Okay, that's a substitution. If you substituted in something for P, something for Q, and something for R, the proof would go through. So that means it's a general pattern that we can use again and again and again. How would that general pattern look in a proof? It would look like this, is if you had on some line, I'll just write line M, if you had phi arrow psi, line N, it might not be right below M, it may be much further down, it may even be above, who knows, somewhere else, psi arrow theta. Okay, so there's 3 sentences here. Now, in this case, who knows what the dependencies are? So I write gamma sub M, that means whatever the dependencies of line M are, gamma sub N, whatever the dependencies of line N are, it doesn't matter. But then the derived rule you get from the sequent you proved above says, aha, these two things on the right, so these two sentences here, they yield the following sentence. They yield phi arrow theta. So But then all you have to do is copy down the dependencies. So every time you prove a sequent, so you aggregate the dependencies of those two sentences. So basically what the cut rule says is if you can derive one sentence from some other sentences, so in this case here, we derived if P then R from the two sentences if P then Q and if Q then R. What that means is then if you're in the middle of a proof and you have sentences of those forms that we have in the premises here, you can derive a sentence of the form you have in the conclusion below, just copying down their dependency numbers. Okay, so that's one case. And I'll just call this for the rest of this unit, this module, I'll call this hypothetical syllogism. So this sort of transitivity of the conditional, and I'll just write HYP because I'll invoke that again in a minute as a derived rule. So I'll show you how it can be used as a derived rule. Let me just give you one other example that I'll use in a minute here. So first of all, we have proven before that if you have not P, then at some later point you can eventually arrive at if P then Q, depending just on that not P. And the resulting sequent then, which says not P gives you P arrow Q, can conveniently be named positive paradox. Okay, and one last such example, we also know that if you start with premises P or Q and not P, then after some work, you can derive Q, depending just on 1 and 2. And this conveniently, the sequent that this corresponds to then, P or Q, and not P give you Q, can conveniently be called disjunctive syllogism. So positive paradox, PP, disjunctive syllogism, DS. And we had from the last page, hypothetical syllogism, HYP. So these all give us derived rules. The hypothetical syllogism rule says if you have two lines with conditionals, if the consequent of the first conditional matches the antecedent of the second, then you can write the conditional that connects the antecedent of the first to the consequent of the second. So sort of transitivity. Positive paradox says if you have a one line with the negation of a sentence, then on a subsequent line, you can write a conditional with that, the thing that's negated, it is the antecedent, and anything whatsoever as the consequent, that's valid positive paradox. Disjunctive syllogism says if you have two lines, a disjunction and negation of one of the disjuncts, you may write on a subsequent line the other disjunct. In all of these cases, when you bring down the dependencies, you gather the dependencies from the lines that you invoked in these arguments. Okay, good. Let's just use this kind of idea now to quickly write out a couple interesting proofs that might at first seem a little bit difficult, but actually when you allow yourselves to build up as we've done here, they turn out to be pretty easy. Okay, let's start with a sequent. Let's start with a sequent that shows that the disjunction P or Q implies if not P, then Q. Okay? Okay, so now I want to show the conditional if not P, then Q. Now, in this case, the sort of obvious strategy to pursue is assume not P and derive Q. So I'll do that. I assume not P on line 2. Okay. Conveniently enough, as if I designed it this way, aha, this is exactly an instance where we can apply disjunctive syllogism. So in other words, now on line 3, I could just put Q here. I could say from 1 and 2 disjunctive syllogism, and then gather the dependencies. That gives me Q. Okay, again, disjunctive syllogism, I'm not telling you here's a new rule. I'm telling you because if you can prove disjunctive syllogism, then you can invoke it in another proof, as I've just done here. Okay, and now finally to finish this particular argument, that gives me if not P, then Q, where I get to discharge the dependency on 2. So that's then just 2, 3 conditional proof. Okay, so there I get the implication from P or Q to if not P, then Q. Okay, let's try another one. So let's look actually now at something that initially probably looks pretty nasty. That is this sequent here, which is sometimes called chain order, because basically what it says is, strangely enough, if you have two sentences P and Q, either if P then Q is true or if Q then P is true. So one of those two has to be true in any situation whatsoever. Now, why would one expect this to be provable? Well, thank goodness we have truth tables, and you can see very quickly that in particular P is always either true or false, right? So P is either 0 or 1, or if I said it's either true or false, it's 1 or 0. In the case that P is false, the first disjunct, if P then Q, is true. In the case that P is true, the second disjunct, if Q then P, is true. So you can see that depending on whether P is true or false, it just gives you one of the two disjuncts. So I'm now going to take that thought process that I just described in terms of truth tables, and turn that thought process into a proof. Okay, so the first step in the thought process was either P is true or it's false. Okay, in terms of proofs, that can be asserted by the law of excluded middle. The law of excluded middle says either P or not P. Okay, that's something that can be proven, of course, from basic rules. What that means is, since the sentence can be proven from basic rules without any premises, at the end of the proof, there's no dependencies. That means then it can be written on a line like this, P or not P. That's the law of excluded middle. What's happening there is I'm using cut. I'm cutting in that proof. If I wrote the proof out in full, there would be, many lines here at the start of the proof. But the last line of that first segment of the proof would be P or not P with no dependencies. Okay, so now I'm just going to continue this argument to prove that either if P then Q or if Q then P. Okay, so I'll take the two disjuncts and argue by disjunction elimination. So in this case, I'll use not P first. So I'll assume not P, assumption. Okay. Now I'm going to use invoke cut with negative paradox. Negative paradox says if I have not P, I can prove if P then anything else. So that gives me P arrow Q. Okay, so from 2, because as with any use of cut, I just copy down the numbers from the left of the lines I invoke. Okay, so this is from 2, negative paradox. Okay, and now I'm just going to add back in the disjunction if P then Q, or if Q then P. Okay, so that's 3 disjunction introduction. Okay, and now I start the second half of my disjunction elimination that I'm going to do. So I assume now P. Okay, so that depends, of course, new assumption, so it depends just on itself, 5. And then now I'm going to use the other. So I just use negative paradox back on line 3. Now I'm going to use positive paradox, which says if I have P, then I can get if anything else, then P. So if Q, then P, so that's 5. positive paradox. And then again, now I'll just do this OR introduction. If P, then Q, or if Q, then P. So that's 6, OR introduction. Okay, so now I'm going to have a big OR elimination. So on line 1, I have P or not P. From one of the disjuncts, I get the conclusion I want from 2 to 4. Then from the other disjunct, P, I get the same conclusion on line 7. So now I can just write that conclusion, if P then Q, or if P then Q, or if Q then P. So that then is 1, 2, 4, 5, 7, disjunction elimination. Now go back and let's tabulate our dependency numbers here. So we carry down the dependencies from the disjunction. That's on line 1. There are no such things. Then we take the dependencies at the end of the first subproof, so on line 4, but we delete the dependency on the assumption line 2, so that leaves us with nothing. And then finally, we take the dependencies from the end of the second subproof on line 7, but again, we delete the assumption from that subproof, line 5. So as desired, the final answer here is no dependencies. So in other words, that thing on the last line is a tautology. It's something that can be proven from no dependencies. Okay, we used here cut 3 times. On line 1, we cut in the proof of excluded middle. On line 3, we cut in the proof of negative paradox. And then on line 6, we cut in the proof of positive paradox. All of these could be written out in full. If you did so, I imagine this proof would be something like 25 lines or something like that. So this just shows there's a proof, but we've given a summarized version of it. Okay, let's do one more proof that involves these kinds of moves where we cut in proofs we've already done. And let's prove in this case, let's prove the transitivity of the biconditional. Okay, so biconditional, so let me rewrite this, I just did here. So biconditional, Q if and only if P, P if and only if R together yield Q if and only if R. Okay. Okay, now if you look in chapter 4, you'll see that biconditional, the double arrow, it's not really a new connective. It's just supposed to be the conjunction of 2 conditionals. And so the rules we're permitted to use with biconditional is we're just permitted to unpack it. So if we have Q if and only if P, that turns into a conjunction. If Q then P, if P then Q. So if Q then P, and if P then Q. So that's one elimination of biconditional in favor of the 2 conditionals. So that depends just on one. Okay, in short, what's going to happen now is I'm just going to get all 4 of these conditionals written out. So I have if Q then P, if P then Q. So these are both by just taking off the conjuncts from line 3, 3 and elimination, 3 and elimination. So that's just, we've unpacked 1 now into its bits. And now we're going to unpack 2 in the same way. So P if and only if R becomes if P then R. And if R then P, so that's line 2, biconditional elimination. And then again, if P then R, 6 and elimination. If R then P, 6 and elimination. Okay, so now on lines 4, 5, 7, 8, we have our 4 conditionals. And here's what we want to do is we want to show that Q if and only if R. So we want to show if Q then R and if R then Q. Okay, and if you look at those 4 sentences on 4, 5, 7, 8, you see that 4 and 7 together using transitivity of the conditional give you if Q then R. And you see that 8 and 5 together give you if R then Q. Okay, and we already proved earlier in this lecture, we proved the transitivity of conditionals, so I'll just invoke that now. So as I just said, we have 4, Q then P, 7, Q then R. So 4, 7, hypothetical syllogism. Okay, now copying the dependencies of those 2, 1, 2, and then 8, R then P, 5, 8, 5, hypothetical syllogism. Again, 1, 2. And so finally, line 11, we can put these 2 together. Q then R then Q. So Q then R and R then Q. 9, 10, and introduction. And that by definition is Q if and only if R. So 11, biconditional introduction. So we introduced the biconditional because we had the conjunction of the 2 conditionals. Depends on 1, 2. Looking back now, yes, that's what we wanted. We wanted to show that from 1 and 2, from Q if and only if P and P if and only if R, we can get Q if and only if R. Okay, so in this particular proof, the use of hypothetical syllogism saved us a little bit of work. It wouldn't have added many lines to just go ahead and prove prove that the transitivity of conditional in the middle of this proof. But this illustrates just in general how one can cut in proofs one has done before into a new proof. Okay, so that's it for this discussion, and we'll continue to talk about truth tables in the next session.